Now we have a 3 kilogram mass and a hanging weight hanging over a pulley with a mass of 1 kilogram, a weight therefore of 9.8 newtons. And this is at what we might call a tipping point from stationary to accelerating. As stated, as soon as we get to 1 kilogram, this thing will begin accelerating. And the acceleration is given to be 120 centimeters per second squared. What we're trying to figure out then is what the force exerted by friction is, both in the case where it's stationary with 1 kilogram and in a case where the system is accelerating at 120 centimeters per second squared with a 1 kilogram mass here. And let's just talk a little bit about the friction. If we graph the frictional force versus the applied force being the force that's applied on this mass in this direction by whatever weight we're holding here. Okay, the applied force, if the applied force is 0, then the frictional force is going to be 0. There's no friction. If there was a frictional force, well, in what direction would it act? A frictional force has to act in the direction opposite the tendency to move. Okay, and there's no tendency to move. There's no friction. If we have no weight over here, this thing's just resting on the tabletop. Now, if we start adding weight and gradually add weight from 0 up to 9.8 newtons, friction is going to hold this thing stationary, meaning that friction can exert a force equal and opposite to any applied force up to and maybe including 9.8 newtons. Okay, now, I guess the way the problem stated, right up to but not including 9.8 newtons. So the force of friction will go up as we add weight, as we add an applied force, as we increase the applied force on this 3 kilogram object. And that's going to be a linear increase because the frictional force is just going to be equal in magnitude to this force. Now it'll be equal and opposite, but I don't have arrows over these. I'm just talking about the magnitudes of these forces. So the magnitude of the frictional force will equal the magnitude of the applied force. But as soon as we get to 9.8 newtons, this thing begins accelerating at 120 centimeters per second squared, meaning that the frictional force instantly drops and then remains pretty much constant. Now this is a model of frictional forces. Frictional forces are much more complicated than this simple model would indicate. What I've said about the static friction is true. Kinetic friction does depend a little bit on velocity and a number of other factors. The way it depends on velocity depends on other factors, the types of materials, the smoothness of materials, and so forth. But the model is simply that the frictional force drops and remains constant then as we continue increasing the applied force. Okay, so the main fact here is that the frictional force will drop to some value here as soon as the object breaks free of the stationary contact with the surface. So if we're moving, the acceleration is 120 centimeters per second squared, which means what? That we can calculate the net force. Okay, the net force on this entire system is what? It's got to be 4 kilograms times 1.20 meters per second squared, or 4.8 newtons. Now we could calculate the net force just on the 3 kilogram mass, but it turns out to be a little more convenient to treat the system as a whole. Now, the system as a whole is subject to the 9.8 Newton force on the 1 kilogram mass, plus the force of kinetic friction. And I should have arrows over these, and I'll indicate that we're taking the positive direction to be the direction that rotates the pulley in the clockwise direction. That usually wouldn't be taken to be a positive direction for rotation, but we're free to make that direction positive in this case. Okay, so the net force is this plus the frictional force, which means then that the frictional force is F net minus your 9.8 newtons. And of course, F net is your 4.8 newtons. 4.8 newtons minus 9.8 newtons gives you negative 5 newtons. So and I can put arrows in these because, again, we're making the forces positive or negative. It's specifying the direction. Okay, so the frictional force is then going to be negative 5 newtons. It's going to have a magnitude of 5 newtons. So stationary, with 1 kilogram, the net force is 0. The frictional force is negative 9.8 newtons when it's stationary with the 1 kilogram mass. Once it starts moving, the frictional force is negative 5 newtons, and the net force then, well, we see is 4.8 newtons. And we could calculate the coefficient of kinetic friction by dividing the 5 newtons we have here by the 29 newtons approximately. So approximately 30 newton weight of the mass here. Because the normal force, the mass acts down with about a 30 newton force, normal force acts up, giving us a 30 newton normal force and a 5 newton kinetic friction force. Divide the 5 newtons by the 30 newtons, we get 1/6 of 0.167 approximately as the coefficient of kinetic friction. Now, it wasn't asked, but I decided I would want to add that just for future reference. So I've added the calculation of the coefficient of kinetic friction being the frictional force, the 5 newton frictional force divided by the normal force between the object and the surface, and that gives us 0.17. We don't include the 1 kilogram here in the calculation of the normal force because the 1 kilogram mass here makes no contribution to the normal force. Okay, the normal force is just the force required to support the 3 kilograms. Also, there's an inequality involved here. Static friction, the force of friction is less than or equal to the coefficient of static friction times the normal force. And I say as needed, meaning that as I need more and more frictional force to hold this thing stationary, the frictional force can continue to increase until it's equal to the coefficient of friction times the normal force, and then the frictional force is not going to be sufficient to hold the object stationary. So, reason for the inequality. Don't make the mistake of thinking of the frictional force as equal to the coefficient of friction times the normal force. It's only equal if all that force is required to keep the relative position, to keep the object stationary relative to the surface on which it's sitting.